Okay, we're rolling. So I've got this curve, based on the function f, and it's this polynomial, this quintic polynomial, times this exponential function, so kind of a complicated function. And I'm interested in knowing arc length. So what does arc length mean? It means like distance along the curve. So it's kind of like, think about if you're walking on the red curve, we're interested in a function that accumulates how far you've walked given your current value of x, right? So your independent variable is x coming along here. And for any given value of x, how far have you walked along the curve corresponding to that value of x? Okay, and so to write such an accumulation function, what do I need?
Rate of change.
Good, so whenever we're accumulating a quantity, we've been talking about this all semester, whenever we want to write the accumulation function for a quantity, we need its rate of change, right? And we developed that last time. So, and let's do that. So let's define it as little r sub little s of x. And who remembers what the rate of change of arc length is for x? What was our rate of change function for arc length?
The square root
Good.
of 1 plus f prime squared.
Good. All right. So what about f prime here? I got a polynomial times an exponential function. What do I need for f prime to do that?
The product rule?
Yeah, we'd have to use the product rule, and it would be long. It wouldn't be hard, but it would just be long, and I don't want to type that in. So this is the beauty of technology in GC. If you go to the math menu and you click total derivative, all right, so total derivative is the same thing as the derivative that you've always learned, so it means essentially derivative. And so you get this d dx, and we want the derivative of what? What do we want the derivative of? F, right? So derivative of f with respect to what variable? X. Okay, but then I want that whole thing. I want to put parentheses first. So let's put parentheses. I want that whole thing what? Squared, right?
Squared.
Okay, is this the rate of change function that we derived for arc length?
Yep.
Yeah. Okay, and so now we want to write the accumulation function, which is going to be s as a function of x. What will we do? How will we write this accumulation function?
Assuming you didn't accumulate any arc length previously, it
Uh-huh.
would be the integral of from 0 to x
Okay.
rs of x, or rs t dt, excuse me.
He wants this. What do we think? You agree with him?
Professor?
Yeah, please. Yeah.
Can the lower limit be 0 because x isn't equal to 0 in the definition?
Oh, yeah. I just wanted to show the graph. This isn't the definition. This is graphing it. Right?
Oh, okay.
This is this is for all x. This is just where I'm showing it, where it's showing graphed.
Okay.
Yeah. Okay. Other questions? What do we think? Is this right? Okay. Yes, it is. That's the accumulation function from 0 to x. So when I define a function, do I have to in the next line graph it? Is that required?
No.
No. So a graph is just one representation of a function. There's nothing that says, oftentimes we'll define a function and then we'll graph it. So that's common. We do that a lot. But it's not this like required thing. It's like it's not this thing that you do every time. Like you have to graph your function as soon as you define it. Okay, that's just a separate thing saying that we want to graph that function that we just defined, but it's not a requirement. And in fact, at this point we don't. I just want to ask you about, now I want to know, how far would it be to walk from x from 0 to 2, say. So x from, or 0 to 1. I just want to walk up and down this hill. How will I find out how far I would walk along the red curve up and back down to x equals 1?
S of 2.
S
S of 1.
S of 1. And there it is, 6.85 units. So and those units would be like your x-axis units, right? So 6.8, distance from here to here would be the same as how far you'd go if you walked up that red curve and back down and then stopped at 1. That's S of 1, the accumulation of arc length, right? Okay, similarly, I could do S of 4. And what would that number mean? Okay, and what would that number mean?
Arc length at 4.
What do you mean at 4? Arc length.
At arc length when x equals 4.
And which arc length is it?
Arc length of f of x.
Okay, so but exactly what arc length is it?
From 0 to 4.
Right, so it's the arc length. So it's the arc length starting from 0, up the hill, down to the valley, little hill, stopping there. So it's this arc length here, starting from 0, ending at 4. Okay, what if I want to know how far it is starting from here at 2 and ending at 4. So how would I figure out how long the arc length is starting at 2 and ending at 4? What could I put in?
S of 4 minus S of 2.
Someone said S of 4 minus S of 2. What do we think? Agree with that?
Yeah.
Yeah, so that would be, yep, starting at, so final value, so all the arc length up to 4 minus all the arc length up to 2 will give you the arc length starting at 2 and ending at 4. So this distance right here. Okay, very good. Okay.
Is there a simpler way to write that?
Yes, perfect question. That's where we're heading. So what about thinking about this integral? Is there another way to express that with this integral?
It would just be the integral from 2 to 4, right?
Right, and so what would that represent? So that's representing a different function where this is 2. And what was this value again in our accumulation function?
Isn't it the beginning x value?
Right, so it's where we start accumulating. So an integral from 2 to 4 would also achieve this value, but then that would be like based on a different accumulation function, the accumulation of arc length starting from 2. Okay?
Oh, okay.
Right? So it would be, instead of starting from 0, we're starting from 2, and we integrate from 2 to 4, we get this exact same thing. Let's just show that. So I'm just going to copy this, paste it here, and now I'm just going to put in 2 and 4. And you get the exact same thing. So that would be like the value of a different function, right? That would be the value of S of 4 in a different function, accumulation function that starts accumulating from 2. Okay, go ahead. Yeah.
So earlier we defined r sub s of x, and I know that's a rate of change function. Can you just explain a little bit more what that is the rate of change of? I'm just having a hard time wrapping my head around it.
Arc length. So we derived it last time. We showed where it came from. But
Yeah.
it's the rate of change. It's how fast the arc length is changing as you change an x, right? So as you move horizontally, it's the rate of change of arc length.
Okay, I remember now. Thank you.
So for instance, right here at the beginning, for a small change in x, that rate will be very high, because for a small change in x, you cover a lot of ground. But over here at 6 or 8, for the same change in x, you're covering comparatively much less change in arc length. So the rate of change here would be much lower. In fact, the rate of change is about 1, right? So for every change in x, you're pretty much getting the same amount of arc length change because it's like horizontal. So that rate of change would be about 1. Is it better?
Mm-hmm.
Okay. So what I want
Thank
to
you.
do is I want to introduce some new notation. Okay, so new notation or function notation. Rather than have our function be just a function of where we're accumulating to, we can also put in the parameter, this constant value, for where we start from. And so then our accumulation function becomes a lot more versatile, like it's a lot more general. So rather than say we're going to start at 0, I can start at, say, a, and then I can add that as a new argument in my function notation. So this gives us a more general accumulation function that includes the ability to easily change the starting value. Now notice when I did that, these values went away because now the arguments, it's not matching up. It's now, whenever you use the function s, GC is going to want these two values. All right, so I want to get the same values I had before. How do I change this notation now so I can generate these same arc lengths that I did before? Instead of just 1, now I need
0, 1.
Now I need 0, 1, right? And that's the value we had before, and then I need 0, 4. Okay, and then I need what? Here this would be 0, 4 and 0, 2.
Is that saying 0 to the given value, or is it like a coordinate?
These are both x coordinates. This is the starting value, the starting x value of the accumulation, and then the x is the same x that we had before, right? So where we're accumulating to.
Interesting. Okay.
Does that make sense? All right. So then now this gives us an easier way to compute this. Now how can I compute the arc length from 2 to 4 now? Much easier.
S2, 4.
Right. So now with this new notation, with the starting value, I can just change the starting value to 2, do 4, and lo and behold, I get the same value.
Is this just something that GC does, or is this like?
No, we're telling GC everything here. GC doesn't know what we're doing. We're telling it everything. So now this is a function of 2 variables. So you have 2 arguments, and whenever you call on that function notation, GC is going to want 2 values, and it's going to put the first value there, and it's going to put the second value there and calculate it. Does that make sense?
Yeah, I was just asking if this is like notation that is used in like textbooks, or is it just like GC thing?
Yeah, no, this is multivariable. This is called a multivariable function. This is a universal mathematical thing.
I just wasn't sure.
Yeah. That's so yeah, and it's actually something that you'll go way in depth in Calc 3. So a multivariable function means that you have more than one input variable, and that's a very common thing. Like I said, you'll learn all about that in Calc 3. Okay, so now I want to graph this. I want to actually graph the accumulation of arc length. I want to get a graph that gives me, for every x value, how much arc length I've accumulated along the red graph. So how will I graph the accumulation of arc length for this red graph? What will I type in?
Y equals S of A comma X.
S of. Okay, and so now I want to set, I want my variable just to be x. So I want to set s to what?
0, x.
Yeah, so it'll be 0, x when I graph this. And we can graph that for x greater than 0. And now what do we expect for this? So is this going to be a constant function? Is it going to be a line, a straight line? Is it going to increase? Is it going to decrease? Is it going to do both? So I'm going to turn that off, and let's just predict. If I'm going to graph, starting here, for x values, what the current accumulation of arc length on the red curve is, what will that graph look like? So increasing, decreasing, both. Will it be changing at a constant rate? Will it be horizontal? What do we predict for that?
It'll increase, but not at a constant rate.
Okay, always increase?
Well, depending on the interval that we're looking at, because if we do it from 0 to 2, let's say 1 to 2, we can tell that the rate was decreasing because it's below the x-axis.
Okay, so arc length. Is the rate of change of arc length negative here? Will we get a decreasing amount of arc length when we travel along that?
Possibly, yes.
I would say no.
So no.
Just because, like, I think of it as like walking along the curve, so you're still
Right.
accumulating distance.
Look at the rate function. We're squaring something, adding 1, and taking the square root. What can you say about that rate function?
It's always going to increase.
Right.
The accumulation. The rate will be, right, so the rate will be positive always. This will always be positive. And therefore, the accumulation will always increase. And that makes sense because when we're walking along this, it doesn't matter if you're above or below. You're still always adding on arc length, adding on distance that you walk. Okay? So arc length function, so it's going to always increase. Is it going to increase like constantly, like a line?
No.
No, because we know the rate is super fast here at the beginning. And then like back over here, the rate of change will be much less. So it's going to always increase, but at varying rates. So let's see that. I'm going to zoom out. So is this what we said? And so then looking over here, so now the curve is kind of flattening out. So it has generally a constant rate, but you can see a little bit of change to the rate, you know. But the key thing is a rate of change, or an arc length function, accumulation function, will always just go up and up and up because you're always adding on more bits of curve as your independent variable increases. So an arc length function will be a strictly increasing function.
So regardless of any, sorry to interrupt you, regardless of it being below the x-axis, because we define the rate of the function as 1 plus, and then the square of the derivative, it's just going to be positive anytime.
Well, so think about, we're talking about arc length, right? So if you're walking along this, right, you're walking along. So now are you decreasing the distance you've walked or increasing the distance you've walked?
Because we're accumulating, I guess we're increasing. We keep adding on
So
to
accumulation in general can be increase or decrease. But it's about this quantity. This quantity is marking off, we're keeping track of how the distance along the curve. That's the key. So the distance along the curve, is it increasing or decreasing through here?
increasing.
Increasing. Doesn't matter. So distance along the curve doesn't matter where it is in the plane. As long as you keep going along the path, your distance is always increasing. Does that make sense? And so then then because that's our quantity, then we see that the rate of change function is always positive.
I see. Thank you.
Yeah, sure. Okay, other questions on this? Okay, so we're gonna switch to surface area now. So we've talked about signed and unsigned area as a quantity. We talked about volumes of revolution as a quantity that we can write accumulation functions for. Now we've talked about arc length. So the next one is surface area. So we're kind of doing like a survey of geometry quantities here. So the next one we're doing is surface area. Let me find my... Come on. No. This one. So surface area. Here we go. Okay, so surface area. So a surface can be generated by revolution, just how we generated solids, right? We generated solids by revolution. We revolved a region, and then we accumulated cylinders filling up the empty shell. So similar to that, we can generate just the surface, kind of like just the empty shell itself. So now we're not going to fill it up. We just care about the surface area of the shell that we get. So if we rotated this graph around the x-axis, do you see that you would get something like that? This purple surface. So now, like I said, we don't care about filling it up anymore. We just want to track how much area of the shell, of the empty shell, as, say, x increases. Okay, so if the S is the surface area function for this surface, so capital S is surface area, little s is arc length, capital S is surface area. What would S of AX mean? What would S of AX mean?
The surface area from A to X.
Right, so the surface area generated, so we rotate a curve, and then we're going to start accumulating, say, at A, and then along the way we're going to be at different x values, and for any given x value we'd have that much, S of A of x would be the amount of surface area starting from A up until x. Okay, so we can do that. So in general, we could write the surface area function. What will it be? Surface area accumulation function. Hopefully everyone could do this. What would I write to just generally express this surface area accumulation function?
Go ahead.
You want to do it, or you want me to do it? Doesn't matter.
Yeah, you go ahead.
Cool. So integral from A to X times the rate of change, the rate of change of surface area, which I'm not quite sure what that would be at this moment.
Yeah, that's what we're going to spend the rest of the class kind of figuring out. But exactly right. So it's going to be the integral from A to X of the rate of change of surface area. Okay, and then we're going to use that other variable t. And this was the whole thing. You know how fast a quantity is changing at every moment? Whoops. You want to know how much of it you have at every moment, so that's our integral function, right? So we need to determine the rate of change of surface area, right? If we can come up with the rate of change of surface area, then we can write surface area accumulation functions all day long, okay? So let's do that. Here we go. So I want to let's go back to this football function that we had. So here's this sine curve. Again, this is a sine curve. And remember that we rotated around the x-axis to make like a football shell. And so now for surface area, it'd be kind of like we're trying to figure out an accumulation function for the actual material of the football, like the surface area. So, and we want to think about rate of change. So I want to look kind of at the back view because it's a little bit easier to see. And so here we go. So before, we accumulated volume by filling that shell up with disks, right? And what would the rate of change of volume be in this case? Rate of change of volume would be calculated by what?
Area of the lateral side.
Area of the lateral side? Is this growing in radius? These disks growing in radius?
Area of the base.
Varying in X.
In height, right? So these shells vary in height, and so because they vary in height, the rate of change was the area of the base, so this gold, right? So this gold face, the area. And remember what we said, that rate of change was what? It was like aligned with where we're adding the next little bit of volume, right? Where is volume being added on? Volume is being added on right there along the gold. So if I increase X a little bit, it's like putting a DVD on there, right? It's like putting a DVD on there to increase the volume. And that's why that area was the rate of change. That much area is how much volume gets added per X, right? So the same thing, we want to use the same thing analogy with surface area. If we're thinking just about the surface now, not filling it in, if we're thinking just about the surface, then what quantity is kind of, where is the surface getting added? What quantity would we look at?
Circumference?
She wants circumference. What do you guys think about that?
Yeah.
Yeah,
The area
good.
of
So
the lateral side, right?
not the area of the lateral side, but the circumference, right? So like this surface area is being added at around the rim, right? So surface area is like the outer edge, and so the next little bit of surface area that we would add on would be that outline, that circumference, that rim, right? So you imagine x increasing a little bit. It's like what would it be like adding a rubber band, or super thin rubber band, right? So it's like adding a circular rubber band as x increases. That's how we're adding on surface area to this. The blue, right? The blue is like the surface area, kind of. Okay, so what would then the rate of change be? So then the rate of change of surface area would be the magnitude of that quantity where the surface area is getting added. So anyone, can we kind of come up with a conjecture for the rate of change of surface area then? What would it be?
2 pi times the radius.
Good. Circumference, right? 2 pi r. What is the radius here?
The y value.
Good. And so the radius is y value. But if our function's in terms of x, then?
Would be the function in terms of x.
Yeah, sine x. 2 pi sine x. Okay, so this is just a conjecture based on what we've known before, right? So based on what we saw with signed area and then with volume, we saw that the rate of change is the same as the magnitude of the quantity where the stuff is getting added on, right? What's getting added on? Like a little bit more, like a rubber band for a little change in x would be adding a little bit more surface area. So it's the length, we think it's the length around that circumference. So we can test this by having a shell for that we know the area. So like a sphere. So if we can test this using a sphere. So let's do that. So here, here's the same kind of idea, but it's gonna be for a sphere. So that if I accumulate it from 0, and this is actually to 3, I would get half a sphere. So first of all, what function am I going to need to rotate around the x-axis to generate that shell? What function, if it's a sphere of radius 3 centered at the origin? So what function would that be?
Parabola?
Is that a parabola that generates a sphere?
X squared plus y squared equals 9.
Yeah, so it's going to be x squared plus y squared equals 9. But now I need that as a function of x. I'm actually showing it right here. So if we solved for y, right? So the function values are the y values. If I solved that for y, it would be square root of 9 minus x squared. Okay, does that make sense? So that's this original curve here, out here like this. That is the curve that I would have rotated around the x-axis to form an empty shell. And now we're going to think about just it's not solid cylinders, but like ribbons. So ribbons are going to be accumulating in delta x intervals and generating surface area. Okay, so so we know what that surface area is, and we can check our conjecture about the rate of change being the circumference and make sure that it's right. So let's do that. So I'm going to do a new GC file. And let's do surface area first. So what do we know for sure? What do we trust as the surface area of this sphere? Does anybody remember the formula for surface area of a sphere?
4 pi r squared.
Yeah, so 4 pi. What's my radius?
3.
3. So 4 pi, is that what we want? 4 pi times 3 squared?
One half.
Yeah, so if we start accumulating from 0 out to 3, we're going to get half, right? So we're going to get half of that surface area. Okay, so 56.54. And so we conjectured that, so we're thinking S of A comma X, and we'll just go right to the accumulation function, and we'll put, instead of defining the surface, or defining the rate function first, we'll just put the rule into the integral. So from A to X, here's our new notation, right? Our new notation for accumulation functions. That includes a starting value to keep it general, more general. You can use it more easily. Okay, and so what do we think the rate was?
The circumference.
2 pi times
3.
sine t, right? So we thought that maybe it's the circumference of these circles, then dt. Does that agree with our proposition here, our conjecture?
Shouldn't it be square root 9 minus x squared for f of x?
Yes, exactly. So the radius, let's see, 2 pi. Yeah.
That was for when we were doing it off of the sine function earlier.
The football function.
Oh, thank you very much. So I didn't erase that. Right. This was for the football function. Thank you. I knew something was wrong there. Okay, so we want to instead, so it's still 2 pi y, is that right? But then our y is different. Is that right?
Yes, sir.
Yeah.
Like that? Good. Thank you very much. Someone's paying attention. So instead of sine of t, we want what?
Square root 9 minus x squared.
Yeah. 9 minus t squared. Okay, now are we good? Now to check to see if this is generating the right surface area, what do I type in?
S of 0, comma 3.
She wants S of 0, comma 3. What do the rest of you think?
Yeah.
Here we go. So, is it right?
No.
Not even close, right? Not even remotely close, right? We're off by 12. Okay? And I'll just, before we start hunting for bugs here in GC, I'll just tell you everything we've typed in GC is absolutely correct, and GC is returning everything to us exactly correct. So our problem here is not with keystrokes or a bug in GC. Our problem is with our assumptions, right? Our theory from the beginning. Okay, so we want to investigate this. What's going on here? Why didn't this work? It made perfect sense that as these cylinders are increasing, we would just increase the surface area by the amount of the circumference. And that is generally right, but there's something wrong.
Is it that f of x is the radius, so we need to like multiply it by, or I'm not quite sure, but wouldn't it be like because f of x can also be like negative values? Because we're
well, so when we rotate it around, it's going to be positive. Yeah. So we rotate it around, we're going to get a positive circumference based on a positive radius. So that's not quite it. Any ideas?
Is the original only using one circumference for the entire value?
No, because we're using a function, right? We're doing a function of x. 9 minus t squared will give us that changing radius at every value of x. See that?
Is it because the function fails the vertical line test at x equals 3?
Nope. Okay, these are good ideas, you guys. Everyone's got good ideas, but not quite. So let's take a look at what we assumed. So notice, I'm going to make these a little bit bigger. So these are for, so this is for a bigger delta x. Same principle here, but I'm showing a bigger delta x. So notice that we, as x increased, we were increasing along what? Along these ribbons. And I wish I had a different color. Let me try. Let's hope this works. Let me try red. We were increasing what? Along dx, right? So we're assuming along these horizontal steps. We were thinking about increasing the circumference sweeping out, but the edge of that circumference sweeping out what? With respect to x, sweeping out horizontally. Okay? So no matter how small I make delta x, even when I make it small, I'm still accumulating according to the edges of these ribbons that are parallel to the x-axis. What's wrong with that? There's something wrong with that.
Why would there something be wrong with that?
Well, you can really see it right here. Look, even my delta x is really small. Is this going to be
It's
good?
not following the curve.
Right. It's not following the curve. Do you see that? It's kind of following the curve, but it's still staying parallel to the x-axis. So especially here, you can see it. When the curve gets steep, it's not doing a good job of reproducing the curve. So let me make it big again. So remember, so this is dx. So what about going along dy? Well, no, because that's perpendicular. So remember, that's our dx. This is our dy. So what would be a better choice than instead of sweeping out parallel to the x-axis, the edges of these circumferences, how do we want to sweep out? We want to sweep out with something better that sweeps out more like the curve.
The arc length?
Good, right? So the little hypotenuse of this triangle, what was that? What did we say that was? Remember?
DS.
ds. When we did arc length, remember? That was our little amount of arc length, that little tangent segment. That little tangent segment, now when x gets small, those little tangent segments will fit to the curve. Okay? So instead of accumulating along dx, we want to accumulate along with ds being the change. Okay? So now we don't have the nice right ribbons. For now, I'll call them ribbons. I'm going to draw over here. So before we were assuming using dx means our little ribbons were growing what? Parallel to the x-axis, like that. But what we really want is a ribbon that looks like this. That as x grows, that ribbon grows along ds. And then that ribbon then will generate surface area aligned with the curve. Or aligned with the shell, right? Aligned with that three-dimensional shell. So we want, this is what we want. So we got to do a little development of that right there. Okay, does the premise make sense here? Oh, let's see, I've got two different.
How come this worked when we were accumulating volume, though? Because we were still accumulating, like, curved stuff. But over here, now that we're accumulating surface area, dx's don't work.
Yeah, that's a great question. So, so when things get small with volume, so I think it's because with volume, we're talking about filling in the middle, and at the edges, so like the volume along that edge is 0 because it's two-dimensional, right? But now when we're doing area, we care about the edge because that's where all the area is. Does that make sense? So like volume.
So now the edge is the most important.
Yes.
Like for the change.
Right, and with volume, that edge is trivial. It's actually like 0 compared to the volume of the whole thing.
Yeah, it literally doesn't matter. Okay, yeah, that makes a lot of sense. Thank you.
That's a great question. In fact, I've never been asked that before. All right, so this is good drawings there for that. Okay, so now we've got to kind of talk about these. Where do these things come from? Where do these come from, and how do we use those? Oh my gosh. So, out of time. So we'll just take like 2 more minutes, and then we'll get it done. So, back to my. Where do I want to be here? Text. All right, so I want to show you that same thing happening here. So here, these is based on these new circumference, this new growing circumference, which is based on ds. So it's these things. It's these things. So this is for a smaller delta x now, and you see it's as they grow, they're matching the surface better, and then even smaller, delta x of 0.1. These things, then they fit around that surface like a glove, right? Whereas these, you'd always have that stair step. You'd always have that little stair step no matter how small delta x got. Okay, so so the way that we get those things is from what's called frustums. So where is it? Here. So if you take part of a cone, so this is this, right? See that? Pause. So if you slice a part of a cone, do you see that that is the same thing as this? That's what we need. We need a sliced part of a cone. So to do it, we're going to flatten that thing out. Boom, like that. And so what do we want? The rate of change is going to be now this distance around. Right? So it's still a circumference, but it's based on what's called a frustum. A frustum is like a sliced part of a cone, that's what this is, right? It's a sliced part of a cone. And we're going to flatten it out, and we're going to get the rate around there. But just it just goes back to being ds. Okay, so what was ds? ds was? Our ds was 1 plus that thing squared, right? dx. This was the rate of change of arc length. So ds equals the rate of change times dx. And so rather than using, for our surface area, rather than using dx, we're going to use ds. Let's do it. So here it is. So this is dx, right? So what is ds? ds is this thing we're going to include this thing now, right? So now we're also going to include, so that right there, that's 2 pi r. Okay, 2 pi r now times this square root expression gives us ds rather than dx. So option B, 1 plus. So I should have, let's define that function. Or minus x squared. And now I'm going to do total derivative. df t dt. As fast as I can here. And that thing squared. And what's wrong? Where have I gone wrong here?
Isn't
Oh,
f of x supposed to be
9,
9?
9, 9, 9, 9. There it is. So now that rather than doing it based on dx, we do it based on ds, and we know that ds is this square root times dx. So when I include that part, that changes my accumulating ribbons from these these right angle ribbons to my frustums using ds. And it works. We got it.
Why are you still multiplying by the d, or like 2 pi r? Oh, never mind. That makes sense.
It's still based on circumference, right? So that it's still based on circumference. We still are accumulating here at the edge, right? This is the next little bit of stuff that's added on, but not according to parallel to the x-axis, but according to along the arc length, which is the ds. So it's still 2 pi r. It's still circumference.
Okay. Thank you.
You're welcome.
So, Professor Ashbrook, just to double check. So if ds was m dx, m is the 1 plus dt f of t, because you know the rate of change of arc length, and dx is still the circumference, which is what we're still using.
Are you talking about this? Are you talking about rate of change of surface area? It'll be 2 pi r times square root.
Fucking minutes, like, and now it's been fucking.
And Natasha, can you turn off your microphone, please? So now it's going to be the 2 pi r, but then it's like transformed from the dx ribbons to the ds ribbons. So this is our rate of change of surface area. 2 pi r times the square root expression that we had for arc length.